Okay, so it is my pleasure to introduce Arran Fernandez. So he's from the Department of Mathematics in Northern Cyprus from Eastern Mediterranean University. And he will talk about semigroup properties for multidimensional fractional and integral operators. Thank you very much.
Thank you very much for the introduction. Also, thank you to the organizers for giving me this opportunity to give a second talk in our seminar series. I already gave one back in January, but they kindly allowed me to give another talk today. So yes, I will talk about semigroup properties for multidimensional fractional integral operators. So the term multidimensional, it will be explained, but as a special case, of course, we have one-dimensional cases. Basically, this is all about a semigroup property. We define some generalized operators with many parameters, and we look to see how the operators can depend on those parameters. This is joint work together with two of my colleagues here in Eastern Mediterranean University. So here's the outline of the talk. Because this problem is, the problem itself is quite simple and elementary, but like the statement of it, but it takes a lot of explanation to get to the point to see why this problem is interesting, why it's worth studying. So I'm going to spend probably at least half the talk on these first two sections, which are sort of set up. So we will have some general discussion first, fractional integrals with various possible kernel functions. Then I will focus on a particular type of fractional calculus called Prabhakar, which will make a useful case study. Also more general types of operators, including bivariate and multivariate. Then in the second part, we will set up the main problem to be solved. We'll define an integral operator with a general kernel function, Fox-Wright function. We will discuss what semigroup properties actually mean for this operator. And here there will also be an open problem or a conjecture. So this work is published. It's been published recently in a paper, but in there is a conjecture, there is a condition that we think is not possible. So we've done all the work without using this conjecture. We've classified all the possible semigroup properties. But if this conjecture is true, then the statement of the final result will become much simpler because many of the possible cases would disappear. So that's one reason why I was interested to give this talk here in front of experts from around the world. Maybe somebody can have some idea of how to handle this open problem. Then the main results will be, there is a parameter p, so we're going to go through the easy cases first. P equals 0, p equals 1, p equals 2. The main result is to classify all possible semigroup properties for this operator, and then using it as applications to construct a complete model of fractional calculus in the cases that have semigroup properties. So let's begin with, everyone knows the Riemann-Liouville fractional integral. This is a convolution of the function f with basically a power function, this function h alpha. Now, I just want to think about, why do we use a power function? From the applications viewpoint, I mean, I'm not working in applications, but I'm told that this can be justified because power law behavior is something interesting in modeling. This is something that can be described well by Riemann-Liouville fractional calculus. So this is a useful operator. Mathematically, it's also a natural generalization of both Cauchy's formula for repeated integrals and also Cauchy's integral formula from complex analysis. But I want to think about it in an abstract mathematical way, without saying, where does this come from or how can this be used? But what are the properties of this specific type of fractional, this specific type of operator, let's say, that make it useful to be used as a fractional integral? Because we can think about considering a much more general operator, basically convolution with any function depending on any selection of parameters, alpha, beta, as many parameters as we want, take a convolution, and we could call that an integral operator depending on these potentially fractional parameters. So what makes Riemann-Liouville special? Here's some more examples. Prabhakar fractional integral, I will come back to this, but I just introduced this here. It has 4 parameters. 3 parameter Mittag-Leffler function here is the kernel. Then there is, as defined by Srivastava, Harjul, Jain, an even more general function, the Fox-H function, can also be used as a kernel to define a fractional integral. Then in one of my papers, we studied fractional integral with general analytic kernel. So basically any analytic function you can put in as a kernel. Over here is this capital A function as a series. Apply the analytic function to a fractional power, multiply by a fractional power, and you get a new integral operator. Then even more general, we have the Sonin kernel, as studied by Kochubey, Luchko, and others. So this is with, there are no fractional powers here, there are no parameters like alpha and beta appearing. It's just convolution with a function kappa, satisfying a continuity type property, and a convolution relation giving the function 1. So we've got a whole bunch of different types of fractional integral operators of increasing levels of generality here. We're first looking at a special function, a more advanced special function, analytic function, and then Sonin kernel is like the most general on this page. But among all of these options, all of these different operators, as we know, when you go more general, when you generalize something in mathematics, you lose properties. You lose some special structure from the special cases. So what kind of properties can still be found? And to go back to the original question, what makes Riemann-Liouville special? So let's now think about fractional derivatives. So far we've defined lots of integral operators. What about fractional derivative operators? There are three natural, I feel these are natural ways to extend a fractional integral that's given to a fractional derivative. First is, of course, differentiation as the left inverse of integration. We expect the derivative of an integral to be the original function. We can also think about taking a fractional integral to a negative order. If you take an integral to order -1, that should be a derivative, fundamental theorem of calculus. But going back to the Riemann-Liouville definition, we assume that the parameter alpha is positive, or real part positive. So this integral does not converge if alpha is negative. But if we think of alpha as a complex variable, we can do analytic continuation in alpha, and that can take us to negative order integrals. Another way of defining negative order integrals would be repeatedly differentiating. So if we start with an integral of order 2.5, for example, differentiate 1.5, differentiate again, 0.5, differentiate again, -0.5, and you've got negative order. So there are three possible ways to extend fractional integrals to fractional derivatives. And the beauty of Riemann-Liouville is that all three of these give the same answer. So we define the Riemann-Liouville derivative as using the third one, repeated derivative of a fractional integral. If you look at the orders here, differentiating each time reduces the integral order by 1. So you reduce by n minus alpha minus n. This would be the integral to order minus alpha. So you have this convention, integral to order minus alpha is derivative to order alpha, and then this is the analytic continuation of the fractional integral. Analytic continuation, of course, is unique, so this gives a justification of the Riemann-Liouville derivative as, in some sense, the only natural extension of the Riemann-Liouville integral. Of course, you have Caputo as well. It's more useful for applications, differential equations, but from the pure mathematical viewpoint, Riemann-Liouville has this unique advantage. And of course, the left inverse property, derivative of the integral is the original function on the appropriate function space. So we can say that Riemann-Liouville is a natural, complete model of fractional calculus. You have fractional integrals, you have fractional derivatives, they fit together in this neat way. All three of these possible extensions are there to go from integrals to derivatives. Now I want to talk about Prabhakar fractional calculus, because we have explored what is special, what is nice about Riemann-Liouville, and Riemann-Liouville is not quite unique in this way. So let's look at some other types of fractional calculus. I want to focus on Prabhakar because it does have these nice properties like Riemann-Liouville. Here is the Prabhakar integral, as we defined already. Prabhakar derivative is defined as the repeated derivative of the Prabhakar integral, similar to what we did with Riemann-Liouville, nth derivative, n minus beta, but we also have a minus gamma. Notice this, we are changing the parameter beta to n minus beta, but we also change gamma to minus gamma. What is the reason for this? Well, the fractional derivative is the analytic continuation in beta. See, in the original thing, we assume that real part of beta is positive for the fractional integral. So we do analytic continuation from that right half plane to the left half plane, under the convention that the integral to order alpha minus beta minus gamma delta is the derivative to order alpha beta gamma delta. So both beta and gamma change sign when you go from integral to derivative. We'll see why on the next slide. And we have the left inverse property. So again, we have all three ways of going from integral to derivative: repeated differentiation, analytic continuation, and left inverse. So why is this possible for Prabhakar? It's not possible for all types of fractional calculus. Many fractional integral operators, those three ways of defining a fractional derivative, do not all give the same result. So let's drill down into Prabhakar and understand what's special about this, what properties give this natural extension. Most important property is the semigroup property. So it is a semigroup property in the parameters beta and gamma, which means that when you take composition, alpha and delta are fixed. You have different values of beta and gamma. You take a composition, you add the values of beta, you add the values of gamma. So that's what I've shown here in red, the semigroup property. You have four parameters altogether. The semigroup property is in just two of them. So that's important. There is a restriction on beta, but gamma is free. Gamma can be any complex number, anything you want. If you set gamma to be 0, you get back to Riemann-Liouville. Riemann-Liouville, we know what the left inverse is. So that means we can always find the left inverse to any Prabhakar integral. Put together two Prabhakar integrals, beta and n minus beta, both positive, and then you get n. This is not even a fractional integral. This is an ordinary repeated integral. And then, sorry, I've written 0 down there. That should be a. It's the constant of integration. We're using a. And then, because the nth derivative of the nth integral is the original function, we get a left inverse like this, identity operator. And if we look at what is on the left there, it is exactly the Prabhakar derivative. So the Prabhakar derivative has the desired left inverse property. That's the first one of the three things. By definition, it also has, of course, repeated differentiation of the fractional integral. So the only thing left to look at is analytic continuation. Also, consider this number n that we have introduced. N minus beta should be positive, but that's the only condition. So we could replace n by a larger number, and we would still be able to get the identity. We would still get a left inverse. So you may think this is not natural because you can choose a bigger value of n. You can get a different operator, which is also a left inverse. So why do we choose that one? But actually, for any value of n, even if you take a fractional number n, so this would really be a Riemann-Liouville fractional integral to order n, it gives the same operator as the left inverse. So the Prabhakar derivative here, we've defined n to be smallest possible integer, floor of real part of beta plus 1, but you could take n to be anything that's bigger than real part of beta, and the operator will be the same. Not just the left inverse, the same operator. To prove that, we use the series formula. So the Prabhakar integral can be written as an infinite sum of Riemann-Liouville integrals, like this. The Prabhakar derivative can also be written as an infinite sum of Riemann-Liouville operators. Some of these might be derivatives, some of them might be integrals, depending on whether k alpha minus beta is positive or negative. These two series are almost exactly the same. Just look at what's in blue. Plus beta changes to minus beta, gamma changes to minus gamma. So if you do an analytic continuation of the Prabhakar integral, changing beta to minus beta, gamma to minus gamma, you get the Prabhakar derivative. So from this series formula, we have the analytic continuation property. We also have this independence of the choice of n that I mentioned, because you can see in the Prabhakar derivative formula, n does not appear in this series formula. There is no dependence on n. So you can choose this n to be anything bigger than beta, and you get the same operator with the same formula. Okay, so from this discussion, we've got two things that are vital for producing a natural, complete fractional calculus. something where you can go from fractional integral to fractional derivative in all these natural ways, and it's the same result. A semigroup property and a series formula. So these two things are the key for, as I've written here, reproducing the magic of Prabhakar. With Prabhakar, this magic happens. It's quite a complicated operator compared to Riemann-Liouville. You have 4 parameters, but you still get the nice properties: fractional integral, fractional derivative, composition properties, all the nice things you want because of the semigroup property and the series formula. The series formula is easy to extend to whatever special function you want in the kernel, because as long as it's an analytic function, it has some power series, you will get the series formula, an infinite sum of Riemann-Liouville integrals. So the important problem that remains is to find a semigroup property, or to find conditions for a semigroup property to exist. Let's just think about what semigroup properties we've seen so far. Riemann-Liouville, the operator has just one parameter, semigroup property in one parameter. Prabhakar operator, 4 parameters, semigroup property in 2 of them. So among those 4 parameters, there are 2 which have a semigroup property and 2 which don't. So that's very important. That's what this talk is all about. If there is a semigroup property, in which parameters do we have that semigroup property? Let's say you can have an operator with many different parameters. You have to choose some of them to have a semigroup property, and which sum is possible. Okay. Before we go to set up the main problem of the talk, I want to do one more topic to discuss, which is about how we choose the kernel function. Because if we go back to the Prabhakar integral, which is defined here, we use the 3-parameter Mittag-Leffler function, E alpha beta gamma. But this operator is not just a convolution of f with E alpha beta gamma. We have modified this E alpha beta gamma function. We have put in a power function inside the brackets and another power function as a multiple. So we're not just considering E alpha beta gamma of t as a kernel, we're considering this modified Mittag-Leffler function. So why do we do this modification? What is the reason? The reason is, here is the original Mittag-Leffler function, E alpha beta gamma. Prabhakar integral is defined like this. Now, if we write this kernel as a series, a Taylor series, what is the form of this series exactly? We're taking the thing inside the brackets to the power of n. So we have delta to the power of n, that's a constant, forget that. We have x minus xi to the power alpha to the power n. So we've got an exponent of n alpha. We also have this multiplier, beta minus 1. So our exponent is n alpha plus beta minus 1. And look at what I've highlighted in brown color. That exponent is matching with the gamma function. So if we go all the way back to the beginning, Riemann-Liouville, we had this function h alpha as a kernel, which is x to the power alpha minus 1 over gamma of alpha. So the exponent should be 1 less than what's inside the gamma function. Okay, and that's exactly what we have here, an exponent which is 1 less than what's inside the gamma function, and it's not what we had in the original expression. So we start with this Mittag-Leffler function, look at what's in the gamma, n alpha plus beta. We want to have n alpha plus beta minus 1 as an exponent, so we get that by modifying the function. So what we're seeing here, that's how we get the series formula, Riemann-Liouville fractional integral with this brown function as a kernel. And what we're seeing here is that what's better to use in fractional calculus is not just the E alpha beta gamma function directly, but this modified function, because what's in brown there is a useful function. It's the kernel of Riemann-Liouville. It also has a nice Laplace transform. That's another good property. It's good to have the exponent being 1 less than the argument of gamma. Okay, so now I want to consider a few more general examples going into more than one dimension. As I promised in the title of this talk, multi-dimensional. So here is what we can call a bivariate, 2-dimensional Mittag-Leffler function. There is a double series, there is a Pochhammer symbol with n plus m, and there is 2 gamma functions on the bottom. Then we modify the function like this. powers, instead of just t and u, we have powers of x, powers of y. We multiply again by a power of x and the power of y, and we get, look at these brown terms, we get again a gamma function with a power of x. They're matching. The exponent is 1 less than the gamma argument, and another gamma function with a power of y, again matching. So then we can naturally define a fractional integral operator. This is a double convolution. It applies to a function of two variables, f of x, y, and we define a double convolution of this f with this bivariate function of x and y. So here's an integral operator with 7 parameters, alpha, beta, gamma 1, gamma 2, delta, omega 1, omega 2. And we have a semigroup property in 3 of them, gamma 1, gamma 2, and delta, not the other 4. I'm not proving that here, just I'm mentioning this as an example to illustrate a point. 7 parameters, semigroup property in 3, not the other 4. Now, you may be thinking, we have a double series, we have a double integral, that fits together, bivariate function here, t and u, bivariate function f of x and y, but actually that is not correct. These two things are not connected to each other. So on the next slides, I will show a double series with a single integral and a single series with a double integral. So the connection is not between the number of variables or the number of sums in the function and the number of integrals or the number of variables in this integral operator. The connection is with the number of gamma functions in the bottom, because for every gamma function, remember, we want to have things like this, power of x matching with the gamma function. So here we have 2 gamma functions in the bottom. We want to have 2 powers in the top. That's why we use x and y. So they're not the same variables as t and u. We start with a double series with t and u. We get x and y, 2 variables because of 2 gamma functions. Here we have another double series, but there's only 1 gamma function on the bottom. And then our t and u, we substitute as powers of a single variable x. So from a bivariate function, we get a function of 1 variable, just x. Here in brown is the power of x with the gamma. Then we get a fractional integral operator using this bivariate Mittag-Leffler function applied to 1 variable. Single integral applies to functions f of x of a single variable. This is an operator with 6 parameters, alpha, beta, gamma, delta, omega 1, omega 2. You have semigroup property in 2 of them. Here is a single series, but it has 2 gamma functions in the bottom. So this is just an analytic function of 1 variable, but 2 gamma functions, that means we want 2 powers in the top. So instead of t to the power n, we need to substitute t as powers of 2 variables, x and y. So we take a 1 variable function, we turn it into a 2 variable function, and we define a double fractional integral. So this is again a double convolution. We have a function of 2 variables, f of x, y, and we take the double convolution with this modified function. Here we have an operator with 6 parameters, alpha 1, alpha 2, beta 1, beta 2, gamma, omega, semigroup property in 3 of them. Okay, so just looking at these 3 examples again, the number of gamma functions on the bottom is determining the number of integrals in the final expression and the type of function that this integral operator is applying to, like how many variables this function depends on. The number of sums in the top, like single sum or double sum, the number of variables, t and u or just t, that doesn't really matter to defining the fractional integral operator. So we can use any special function, including bivariate ones, multivariate ones, to create a fractional integral operator. The fractional integral operator may itself be a double integral or multiple integral applied to bivariate, multivariate functions, but there's 2 separate things going on here. So we start with the power series, which has some dimension, maybe double series, triple series, whatever. That determines how many variables the original function is applied to. Single series t, double series tu, triple series tuv, whatever. But the important connection is the number of gamma functions in the denominator determines the dimensionality of the integral operator. So the natural way to define an integral operator based on this kernel is a double integral. The natural way to define based on this kernel is a single integral, because it depends on the number of gamma functions. And that determines how many integrals are used, how many variables the modified function is applied to. So we start from t and we go to xy. We can start from pu and go to x. The number of variables in the modified function corresponds to the number of integrals. And what sort of functions the integral operator applies to. F of x, f of xy, whatever. Okay, so now I've explained the multi-dimensional part of the title. Let's go to firstly defining our general integral operator and then looking at the semigroup property. So the kernel function we're going to use is the Fox-Wright function. This is a very general type of special function. It includes lots of other special functions as particular cases. It's defined like this. We have p different gamma functions on the top and q different gamma functions on the bottom. P and q can be whatever you want. There are, of course, some conditions on the parameter for this to converge, but I'm not going into the details on that. It's just like real part of something is greater than 0. I'm not putting it on the slide. We define, because we have q gamma functions on the bottom, we define a q-fold integral operator. Okay, q different integrals here, and it applies to functions of q variables. t1 up to tq, function of q variables, and this is a q-fold convolution. So we have 2p plus 2q plus 1 parameters. What are all the parameters? We have our little a's, p of them, big a's, p of them, little b's, q of them, big b's, q of them, and a delta. So it's 2p plus 2q plus 1 different parameters. And here is an integral operator applying to functions of q variables. We have modified this Fox-Wright function by substituting in powers here and multiplying by powers there. So it was a function of one variable. We've modified it to a function of q variables. We can take the Laplace transform of this modified function, this kernel, and the Laplace transform of the kernel function is this. This is also the multiplier. If we take the Laplace transform of this integral operator, it is that thing at the bottom times the Laplace transform of f. Okay, so that's going to be important. We will be using the Laplace transform later. Just notice that all the gamma functions on the bottom have disappeared in this Laplace transform because we have made sure that the exponent matches with the gamma function. So when you take the Laplace transform, you get just a power function without any gamma. So we've taken t1, t2 up to tq, Laplace transform to s1, s2 up to sq. Here is the main problem, main question of this talk. What are the conditions to have a semigroup property in some of these parameters? So what sort of semigroup property do we mean? We're taking compositions of integral operators. That is equivalent to taking convolutions of the kernel functions, it's modified Fox-Wright function. And by the Laplace convolution theorem, that is equivalent to multiplying the Laplace transform function. So we're taking convolution of this operator, we want semigroup property, or composition of the operator, convolution of this kernel function, or just multiplying the Laplace transform function. By the way, we have a constant multiplier here, this big C. It's just a constant. I've included in the notation that it can depend on any of the parameters. Right? So this is the main problem. But before we go into solving it, we need some more discussion just to understand more clearly what this is saying. Because what does it mean to have a semigroup property in some of the parameters? We should set up the problem clearly and formally. So I want to consider an example, just a random selection of parameters to show you what semigroup property actually means. So let's say random values, p equals 3, q equals 2. That means you have 11 parameters, and we're going to say a semigroup property in these 5. Okay? So something very important that I'm doing in this talk is color coding. So red is for semigroup, blue is for not semigroup. So every parameter now I'm giving a color. When you see one in red, we should have semigroup property in that. When you see one in blue, we should not have semigroup property. So let's just jump back to Prabhakar. You remember the semigroup property for Prabhakar. We have semigroup in beta and gamma, not in alpha and delta. So these beta and gamma are in red. When you put together, you fix alpha and delta, you put different values of beta, different values of gamma, and you add them together by composition. So let's come back to where we were. Yeah. So here we have the composition semigroup property of the operators. Everything in red. Let's look at little a1, for example. Little a1 and then little a1 prime. When you put them together, little a1 plus little a1 prime. You are adding the semigroup parameters. For the blue ones, they're just staying the same. Look at little a2, little a2, little a2. Delta, delta, delta is the same. Big A1 semigroup, big A1 prime, and the sum of them. So this is the semigroup property for operators. This should be true for all values of the red parameters, but we may need to fix some of the blue parameters. Why is that? Because let's say we find a semigroup property which is true, but only if, for example, delta equals 1. Then that's okay, that's a semigroup property. It's not the most general Fox-Wright function. We need to fix one parameter as delta equals 1, but it is still a meaningful semigroup property in a special case of the Fox-Wright function. So we can fix blue parameters, but it does not make sense to allow fixing red parameters, because let's say you have a semigroup property that's true only when little a1 equals 2, little a1 prime equals 7. So you put together 2 and 7 and you get 9. But that's not really a semigroup property by itself, just with those values, because that just means maybe by coincidence 2 and 7, when you put them together, you get 9. Semigroup property should be true for all values of the parameters that you are adding. The red ones, they get added together. They should be free parameters, can take any value. The blue ones, they can also be free. It will be nice if they can be as general as possible, but for the blue ones, we can fix them if we need to. So again, going with this example, this is what the product, the multiplicative semigroup property looks like for the Laplace transforms. We have a big series, we multiply by another big series, and we get a third one. So the left-hand side is a double series. We're multiplying two series, we get a double series, and we can simplify, because in this case, everything that's inside the power, see the power to the n, power to the m, all of that is blue. So it's the same in all three expressions, which means we can do that thing to the power of n plus m on the left, and put k equals n plus m, and then we get this identity, which should be true for all values of k, or you can have delta equals 0, and then it will be trivially true, because everything is just a constant. Sorry about the background noise, by the way. I don't know if you can hear it, but they're cutting the grass outside. I hope you can hear me well enough. Yes, so this is the thing. In this example, which is just a random example, we're going to go to the main problem soon. In this example, that equation number 2 is what you would need to check if this is true or not. This should be true for all values of the red parameters, but maybe the blue ones can be fixed. C here is a constant. It can depend on the parameters, but it must be independent of k. Okay, so this should be true for all k. K equals 0, k equals 1, k equals 2, etc. Finite sum equals this. So that's the kind of thing we're going to be doing throughout this talk, basically looking at equations like this in gamma functions and seeing whether we can get a contradiction or not. Sometimes we get a contradiction, we say this can't be true, so you can't have a semigroup property like this. Sometimes we get some condition to say that it is true if the parameters are like this. So let's formalize the problem. We write the vector of all parameters as R. So that's a 2p plus 2q plus 1 dimensional vector. We split it into red parameters and blue parameters. So semigroup in the red ones, not in the blue ones. So what does this semigroup mean? We take a composition of two operators like this, red plus red, and blue just stays the same in all three operators. This should be true for all values of the red parameters. For the blue parameters, it's nice to make them as general as possible, but we can fix them. We can fix the blue parameters if necessary. So the problem, the thing we're solving in this talk is to figure out which parameters are red which ones are blue. We have 2p plus 2q plus 1 parameters, and we need to basically split them to red ones and blue ones. So let's do the first two steps first, which are easy. It's easy to prove, just from powers of s in the Laplace transform, that all the blue parameters, sorry, all the big B's must be blue, all the little b's must be red. Okay, so out of this 2p plus 2q plus 1 parameters, 2q of them now are solved. Okay, we know they're semigroup or not. That leaves the little a's, the big a's, and delta. 2p plus 1 parameters remaining to check. And now I introduce a condition which relates to this open problem that I mentioned at the beginning. So for a given natural number p, we have 2p parameters. We say that they satisfy the condition Cp if this is the Cp condition. So we have a product of 2p different gamma functions on the left, product of 2p different gamma functions on the right, and they should be equal for all natural numbers m and n. All values of m, all values of n. So for example, the condition C1, it says that little a and big A should satisfy this equation for all values of m and n. If you set m equals 0 or n equals 0, this is clearly true. But if you put m equals n equals 1, for example, simplest positive case, you get gamma of a plus a times gamma of a plus a equals gamma a times gamma of a plus 2a. Now, that's of course not true in general, but are there any particular constants, little a and big A, which could make this true? And I think that there are not. There is no solution to this, but we were not able to prove it. So here is the conjecture, is that the condition Cp is impossible, except in the trivial case where all the big A's are 0. So we believe that this is true. We believe the condition is impossible, but even in the simple case of C1, we were not able to prove that this is impossible. We tried using Stirling's formula, using all sorts of identities for the gamma function. We tried even combinatorial methods. I don't know whether this could be solved by analysis, by combinatorics, what sort of methods could work here. We tried a lot of things, we couldn't get any solution. It's also possible that this has been solved somewhere in the literature and we didn't find it because it's difficult to search for. There is no kind of name for this. We just called it C for condition. So if anyone knows any literature about this, or if anyone has any ideas about how this might be proved impossible, I'll be very interested to hear it. So now we start on the main results of the talk. We want to consider, we have 2p plus 1 different parameters to consider. And so that's the little a's, the big A's, and the delta. We want to start with small values of p and work our way up. So if p is small, then we have a finite problem. But of course, in general, we can have any value of p. Important fact, if delta equals 0, the operator reduces to Riemann-Liouville. So that's a trivial case. If any capital A, if any big A equals 0, then I call this a reductive case, because let's just go back to the Fox-Wright function here. If you put delta equals 0, then the series just reduces to one term. So it's one power function, which is Riemann-Liouville. If a big A equals 0, then one of the corresponding terms on the top is going to be just gamma of little a, which is a constant. Constant multiplier doesn't matter. So that means we have reduced the p gamma functions on the top to p minus 1, because one of them just became a constant. So I call that a reductive case. And of course, later on, we're going to use induction on p to solve this problem. So reducing p to p minus 1 is going to be a very useful thing. So let's start with p equals 0. We have 2p plus 1 parameters in general. So now it's just one parameter, which is delta. Two possible cases, delta red or delta blue. Delta red means we should have this identity. That's true. That's just the binomial theorem. So we do have, in the case p equals 0, we do have a semigroup property in delta. Delta blue means we should have this identity, which is false, except in the trivial case of delta equals 0. Okay, so now the p equals 0 case is done. Red is true, blue is false. Simple. Now p equals 1 case, we have 3 parameters, little a, big A, delta, and that means 8 possible cases, because each of these 3 parameters can be either red or blue. So 2 to the power 3, 8 cases. In every case, the condition can be reduced to the following finite sum identity. That should be true for all values of k. There's a constant c independent of k. Now, the double prime notation, this is another notation introduced just to make the notation a little simpler. Double prime means the following. Let's take delta, for example. If delta is blue, that means no semigroup, then delta, delta prime, delta double prime are all the same. If delta is red, that means semigroup, then delta and delta prime are 2 independent, and delta double prime is their sum. So this is again what we saw with Prabhakar. You have alpha and delta were blue, the fixed parameters, the non-semigroup parameters, they just have the same value in all 3. The semigroup parameters, the red ones, you take beta 1, beta 2, and then their sum, or in this case, beta 1 prime and their sum, whatever notation we use. So that's the double prime notation, because I'm not saying yet which ones are red, which ones are blue, but this is what we have in every case. And then if, let's say, if little a is blue, then this is just a. If big A is red, then this is going to be a plus a prime, and so on. When we put k equals 0, this should be true for all values of k. Put k equals 0, you solve for the constant multiplier. It's always equal to this. It's a gamma function if a is blue, to a beta function if a is red, little a. Now, let's go through these 8 cases. We consider each time k equals 1, and in many cases, we can get a contradiction. Firstly, all of them red, semigroup property in all 3. Then this relation should be true for all values of all the parameters. That is false. Second case, little a and delta red, big A blue. That means we should have this for all values of little a, but that can only be true if big A is 0. I mentioned that big A 0 is the reductive case. It reduces to p equals 0. P equals 0 we already solved, so we're going to ignore that. Case 3, big A and delta red, little a blue. This should be true for all values of big A. Again, is false. So far we've got 2 false and 1 reductive. Case 4, this one is interesting. Delta red, both the A's blue, and that reduces to this relation, which is the condition C1. Remember, we conjectured this to be impossible, but we were not able to prove it. So case 4 is still possible until that conjecture is proved. Case 5, all of them blue. That's only possible if delta equals 0. Delta equals 0 is trivial. It gets back to the Riemann-Liouville case. Case 6, again, only possible if delta equals 0. Case 7, only if delta equals 0. So cases 5, 6, 7, we can say are trivial. They don't give any interest in semigroup property. Case 8 is the interesting one. Little a is red, big A and delta are blue. Then the relation becomes this. When you put big A equals 1, that is the true van der Monde identity, which is true. So when A equals 1, this is true. If A is not 1, it's false. So when we fix the big A, we're allowed to fix big A because it is blue. Okay, blue parameters can be fixed if necessary. So we fix big A to be 1, and then we get a true semigroup property. So now we've done all 8 cases, summarized in a table. We have case 1 and case 3 are impossible. Case 2 is reductive. Cases 5, 6, 7 are trivial. The interesting ones are just cases 4 and 8, which I put in bold. Case 4, we conjecture is impossible, but we must include it as a possibility. Case 8 is a real semigroup property for sure. So here we have a lemma summarizing the results for p equals 1. We exclude the trivial and reductive cases. We have only 2 possible semigroup properties. One is in the little a and little b parameters, and one is in the delta and little b parameters with the C1 assumption. Now let's go to p equals 2. In the p equals 2 case, you've got 5 parameters, little a1, little a2, big A1, big A2, delta, 32 cases. That's too many to do by hand. but there are some tricks which will let us reduce the work. So again, the condition in every case reduces to this. Finite sum equals this k expression. Double prime is defined as before. So that means a different thing according to whether the parameter is red or blue. All the parameters are black here because we have not specified yet which ones should be red, which ones should be blue. We will consider these cases in the next slides. When you put k equals 0, you find the value of the constant multiplier c. Again, gamma function for blue, beta function for red, but now it's a product of two. One for little a1, one for little a2. So in the previous case, we saw that big A can never be red. There's no semigroup in big A. I'm going to start here by assuming a semigroup in big A2. Assume big A2 is red and try to reach a contradiction. Now, the good thing about red parameters is that the semigroup property should be true for all values of the red parameters, which means we can just set big A2 to be 0, and then we reduce to the p equals 1 case, which is already solved. We know what happens on p equals 1. It's only two possibilities, case 4 or case 8. So with this assumption, big A2 red, we didn't assume anything about little a2, and that's not included in the p equals 1 case. The p equals 1 case is covering little a1, big A1 delta. So we've got two cases for little a2, blue or red, and we've got two cases for the other parameters, case 4 or case 8 from before. So 4 options to be considered. I'm not going into details because I don't have time, but it turns out that all of these give contradictions. So from big A2 red, we get a contradiction. That means big A2 must be blue. By symmetry, big A1 is also blue. So we've solved the big A's, and those 32 possibilities now reduce to just 8. We have little a1, little a2, and delta. So 8 is small enough we could go through them one by one, but there's still another trick to be used. If we assume little a2 is blue, then the k equals 1 case gives this relation. And now every term in this equation is a multiple of gamma little a2, gamma little a2 plus big A2. Those two factors appear in every term, so we divide by them and we get exactly the p equals 1 case. So again, we've reduced to the previous case, which has only two possibilities, case 4 and case 8, and both of those give possible semigroup properties under some assumptions. So case 4 means delta is red, everything else is blue. We've assumed little a2 is blue, here little a1 is blue as well. So delta red, everything else is blue. We need C2 assumption. Case 8, little a1 is red, everything else is blue. And here we need the following relation. The little a1s we can cancel by true van der Mond. And then we get the C1 condition for little a2 and big A2. So these are the possibilities when we assume little a2 is blue. By symmetry, assume little a1 is blue, we get a similar set of options. The only case left to check is if little a1 and little a2 are both red, and that requires this from the k equals 1. Because red parameters can be set to any value, they should be general, we can let them tend to 0 and we get a contradiction. Okay, so now we have a lemma, cover all the p equals 2 cases, excluding trivial and reductive cases again. The only possible semigroup properties are either little a1 and all the little b's, little a2 and all the little b's, or delta and all the little b's. All three of these require either C1 condition or C2 condition. So if the conjecture is true, then there is no possible semigroup property with p equals 2. Okay, now we come to the main result of the talk, main theorem. This is for any given p, excluding trivial and reductive cases, the possible semigroup properties are as follows. Either one single little a and all the little b's with a CP minus 1 assumption, or delta and all the little b's with a CP assumption. The proof is by induction. P equals 2 we've already done. So we assume true for one value of p, we go to the next value. There are 2 to the power 2p plus 1 possible cases. We've seen before 2, 8, 32. In general, it will be this power of 2. We only need to check 5 things. So by some tricks, we can reduce it to 5. And we only need the k equals 1 case to reach contradictions when there is a contradiction. If we assume a big A is red, then we get back to the inductive hypothesis, the p-1 case. If little a p is blue, or if little a p is red, both cases we get a contradiction. So I said 5 checks, this is the first 2. So from this contradiction, we know all the big A must be blue, and we've reduced our 2 to the power 2p plus 1 cases to just 2 to the power p plus 1 cases. Next, we assume a little a is blue. We do some cancellation, again use the inductive hypothesis. There's only 2 possibilities from the inductive hypothesis. Either a single little a is red, everything else blue, or delta is red, everything else blue. And then we get, as required, the condition either Cp minus 1 or Cp. 1, 2, 3, 4, 5 checks. So the last thing to check is if all the little a's are red. We assumed one is blue to get this. If you assume they are all red, you get a contradiction. Again, I don't have time to go into details. I'm just showing a sort of sketch of the proof. So this is the end of the proof. Here is a table of the possibilities. We have red parameters on the left, blue parameters in the middle, and required assumption, if any, on the right. So this table is split into 2 parts. The first 2 rows, they are definitely possible semigroup properties. The lower rows, they require a CP assumption. So if our conjecture is true, then the only possibilities are the first 2 rows. Okay, so that's the main result of the talk, but because we motivated this in terms of constructing a complete model of fractional calculus, going from the integral to the derivative, seeing how everything fits together, should spend some minutes at the end doing some applications of this result to see how did it actually look. We have 2 possible semigroup properties, p equals 0, p equals 1. I didn't go into detail on the others because we think they're not possible. So if p equals 0, here is the multivariate fractional integral operator, Fox-Wright function size 0q. Multiple Laplace transform looks like this. Now, interestingly, you can see that all the semigroup parameters appear as exponents. And that's why you have semigroup in those parameters, because it is an exponent. When you multiply together, you are adding the exponents. Here's the semigroup property, and here is the series formula. Now, how do we define the fractional derivative? We define it like this. It is a repeated partial derivative of the fractional integral, with the appropriate values of the parameters. Series formula, this proves that the definition is independent of the choice of these n's, same as for Prabhakar. If we compare the series formula with the previous one, here is the series formula for the integral. We replace delta by minus delta, all the little b's by minus little b's, and we get the series formula for the derivative. So this is the left inverse, is the analytic continuation, where we negate the semigroup parameters, the delta and the little b's, and it is given by, in the definition, repeated derivatives of the fractional integral. For the p equals 1 case, here is the multivariate integral operator, psi 1q. Multiple Laplace transform, again, all the semigroup parameters, the red things, appear in exponents. The little a and the little b's, they're all exponents. You have this semigroup property. And here is the series formula. It looks very much like the Prabhakar series formula, except that you have a multiple Riemann-Liouville integral there. Here is the fractional derivative, again defined by a repeated partial derivative. And here is the series formula for the derivative, which is again looking the same as before. I go back. This is the same, just you replace little a by minus little a and the little b's by minus little b's. So this is the left inverse, analytic continuation, and it is given by repeated derivatives of the fractional integral. So let's move on to conclusions. We've considered 2 questions. Firstly, what makes a natural complete model of fractional calculus, natural interactions between fractional integrals, fractional derivatives? And then that led to the main question, when can we get a semigroup property in some parameters for a fractional integral operator? And we found answers. A series formula and a semigroup property are the key properties to get this natural extension. The dimension of the fractional integral, the number of integrals involved, should equal the number of gamma functions in the denominator for a nice natural operator. We considered a very general fractional integral operator, Fox-Wright function kernel, potentially multivariate operator. We completely classified all possible semigroup properties in any possible selection of the parameters. In each case which has a semigroup property, we can construct this natural complete model of fractional calculus, integrals, derivatives, nice relations. If conjecture is true, it's a very elementary conjecture, okay? It just involves gamma functions. The conjecture is not involving fractional operators, integrals, derivatives, anything. It's just gamma functions. If that conjecture is true, there's only two ways to get a semigroup property, p equals 0 or p equals 1. And if you go for the p equals 1 option, you take the one-dimensional case, q equals 1, then you get exactly Prabhakar. Four parameters, it is the Prabhakar integral, it is the Prabhakar derivative. So we can see that Prabhakar is somehow special. Everything else with a semigroup property looks like a multivariate version of Prabhakar. There are so many relevant references here. I wanted to fit them all on one slide, so I cut them down. The red one at the bottom, that is our paper that this talk is based on. It's already appeared online, doesn't have a volume number yet, Studies in Applied Mathematics. Funny story about this is that when we first started this project, we thought it was going to be easy to classify all these semigroup properties. We were planning to send it to Applied Mathematics Letters, which has a 6-page limit. So we thought 6-page paper, we can do this. Then just more and more and more and more complications arose, and you can see it ended up as 42 pages paper. First 6 references are just about kind of general operators, general classes, analytic kernels, and then some work of Kiryakova and Srivastava on operators with Fox-Wright kernels. Then we've got 4 papers on bivariate and multivariate, Mittag-Leffler functions, fractional operators, which are relevant to this. And of course, number 11 is the paper that this is based on. So that's the end of my talk. Thank you all for listening.
Thank you very much for some nice talk. Are there any questions, either in the audience or online?
I have a question for how to. Can I ask how it works here? How it works here?
Yes.
If you can just
you are asking question.
Yeah. Arran, usually convolution type fractional derivatives are related to have a probabilistic interpretations, like there is a subordinator and we can construct this from some sort of subordinate, and that help us to solve some problem. We have at least in some cases probabilistic interpretation of your generalized fractional derivatives. I mean, in terms of subordinators of some degree subordinate.
Unfortunately, I don't really know about probabilistic interpretations. I'm not working in the probabilistic stuff at all, so I don't know, but I would be interested to find out. Maybe some people, because I think this general operator that I've looked at is not something that I've defined for the first time. Like Kiryakova, maybe Professor Mainardi has studied operators with this type of Fox-Wright kernel. So maybe there is already probabilistic interpretation of this existing in the literature, but I don't know, sorry.
Thank you.
More questions? Okay, then thanks, Arran, again. Now we need to switch to the next talk because we have 2 consecutive talks.
Yes, I will stop
So
screen
thank you
sharing.
again.
I think the next talk is going to be in person.
And,
Spaniards there in Cambridge. How do I stop?